So, welcome back. We are ready to start with session one, which is development in analytical methods for micro and nanoplastics. And here we will have three talks, and the first one is a keynote lecture from Douglas Gilliland, Joint Research Center, EU Commission. The title of the talk is Definition of Micro and Nanoplastics and Analytical Challenges. So please, Douglas, you have the floor.
Thank you very much. My name is Douglas Gilliland, and I work at the European Commission's Joint Research Centre in Yspres, Italy. And I would like to thank the organisers for giving me this occasion to participate in this important. I'm getting a sound bouncing back. I've been working with analytical methods for nanomaterials for a number of years, and more recently I've begun to apply this experience to the challenge of micro and above all nanoplastics. And today I would like to provide you with an overview of definitions of microplastics and the analytical methods for their analysis. Now, today you are to consider an emerging aspect of a major economic, environmental and technological issue. The use of plastics has been going on for 6 decades, and although in recent years there has been increasing efforts to recycle and retain plastic, the cumulative effects is that there are still billions of tons of plastic lost to the environment. Now, whilst the exact fate of all these lost materials has still to be understood, there is no doubt that a significant portion of this plastic will at some point be present as free particulate microplastics or even nanoplastics. As we're well aware, a portion of this plastic will be in microplastic form, either as manufactured or as a result of fragmentation of microlitter by physical, chemical, or even biological processes, making it easier for them to enter the food chain. Now, while physical and chemical mechanisms are known, although poorly understood, there is still limited quantified information about widespread occurrence, distribution, and fate of micro-sized particles, and even less about the smaller submicron particles. Such is the difficulty of the detecting nanoparticles that their formation environment has only recently begun to be confirmed. This process, although usually attributed to chemical weathering, may, in the context of microplastics in food, also be occurring by other means which are of particular relevance in relation to food. A study of microplastics ingestion by Arctic krill, an animal whose unusual digestive system involves mechanical grinding, appears to show an ability also to produce nanoplastics from larger microplastics. Sorry. As we can see here, these microkrill, when they were given microplastics to eat, the excreted products afterwards contained also particles, but also it was found that there were a significant number of smaller particles which has been produced from the larger particles. I cite this particular example as Arctic krill is a major food source for higher marine life forms, and as such it may be a source of nanoplastics and also a vector for transporting it into the larger food chain. It's noteworthy that the biomass of krill in the ocean is thought to be several times greater than that of the entire human population. Now, irrespective of how they are produced, once the primary or secondary microplastics are present in the environment, many different potential paths exist along which the plastic can move through the environment and ecosystem and eventually back to humans. The paths and their relative importance are varied and not well understood, but may potentially interact with other factors such as chemical pollutants, biological bacteria, all of which could alter potential risks that present through interactions with humans. Now, beyond the scientific literature, the media has continued to bring the subject of microplastics to the attention of the public, often with alarmist headlines. Such reporting may be scientifically questionable, but at least has produced a stimulus that the research community, now supported by politicians, and events such as Colloquium, have the opportunity to move towards a more balanced and informed investigation of the phenomenon. Although microplastics and possibly also nanoplastics are ubiquitous in the environment, and the hazards which they may present to the environment and humans have been hypothesized, the difficulties in detecting, characterizing, and quantifying these real materials remain a major challenge when attempting to link cause and effect at realistic exposure levels. In many ways, there are similarities with the work of nanotoxicologists, but with the added complication of having hugely heterogeneous materials with particle size ranges spanning 6 orders of magnitude and little access to real or even realistic test methods. The growing public awareness on this subject, driven by intense media attention, has highlighted lack of knowledge in the area, but has also provided the political will to try to better understand the realities of the potential risks and hazards of micro and nanoplastics. Now, while these reviews consider many aspects of the subject and highlight the knowledge gaps, a recurring theme is that many of the gaps result in part or in whole from limitations of current analytical methods. This, for microplastics, attributed in part to the uncertain quality and reproducibility of the data, resulting from the lack of method harmonization and quality assurance tools, while for nanoplastics, the lack of broadly available established methods remains a critical problem. More specific consideration of the current knowledge in relation to food show the same trends. Now, while there are increasing numbers of reports of microplastics in food in the literature, the overall picture remains clear due to the complexity of the problem, the range of possible products, and above all, because of the very variable quality of the data presented and lack of standardization. Often data is presented about particle numbers and types of polymers, but with little information about other characteristics such as size and shape, all of which may have relevance to hazard. This may be a consequence of complexity of samples to be analysed, but also the uncertainty about the relevant particle characteristics, compounded by the current lack of harmonisation and quality control criteria and tools. As a minimum, it would be highly beneficial to establish a critical level of characterisation, which should be respected in scientific publications. Hopefully, activities such as this meeting today will help to promote such developments in the future. Now, while reports of microplastics in food have been steadily increasing for some years, more recently studies have begun to examine food contact materials, sometimes with headlines emphasising the consumption of millions of particles per day. Now, while this may be technically correct, it may be put in context by considering the approximate mass of plastics. In this case, calculations would indicate the real mass of plastic corresponds actually to a small fraction of a milligram. Despite the tendency towards hype in this area, the widespread use of plastic food contact materials and the importance given to legislative control of the sector make this an area of relevance, which we have begun to look at with some examples where contact in use could potentially result in the release of microplastics or nanoplastics. We've looked at 4 examples. Ice bags, where we hypothesized that mechanical effects could produce particulates, perforated or textile bags for rice and tea by thermal effects, and bottled water, where mechanical release could result in repeated opening or could result from the repeated opening and closing of the bottle cap. Now, with the exception of the ice bags, our release of small micro and submicroplastics could be referred to in all cases, but only in the case of the nylon tea bags was it sufficiently high to permit a determination of mass. In the case of nylon tea bags, a portion of these measurement was thought to originate from solubilization, reprecipitation of oligomeric materials rather than fragmentation. It's not clear whether any of these is a significant source of microplastic in food, but it represents an area to evaluate more closely in the future, as this would be an avoidable source of microplastics. A critical step in future development will be to have a widely accepted understanding of what constitutes microplastics. Sorry there, I've got some confusion. A critical step in future development will be to have a more widely accepted understanding of what constitutes microplastics. Till recently, this was more a common understanding which has developed starting from the first use of the term microplastics by Thomson in 2004. Since then, there's been a gradual evolution of terminology, although till now there's still no universal agreement on even the most fundamental issue of size or size range, although an upper size of 5 millimeters is increasingly accepted. There's much discussion about a possible lower size limit, and even whether there should actually be a limit imposed, given the lack of any clear-cut size cutoffs with respect to particulate size existing in the environmental or biological response. Recent considerations by Gigot, who previously put forward the definition of environmental plastics, which included also a consideration of its colloidal behavior, has suggested that the distinction between microplastics should not be rigidly based on size or composition, but possibly on other properties such as transport properties, interaction with light and natural colloids, bioavailability, and diffusion times for the release of plastic additives. It's possible this alternative view may have to be considered further in the future, where more is known about the way which properties impact the interaction between nanoplastics and biological systems. Now, with increasing concerns about the effects of microplastics and the prospects of eventual legislative activities, there has been an increasing move from a common understanding of microplastics to a more detailed and broadly accepted terminology or definition, which goes beyond simply size and composition. Now, this topic alone would merit a detailed presentation, so I will limit discussion to listing some of the principal criteria which have been identified in the course of detailed considerations, such as those undertaken by Verschuur and later by Hartmann. The principal criteria are really related to composition, polymer additives, copolymers and composites, and also the properties: solid state, solubility, size, shape and structure, and possibly even color, as this may influence, for example, the eating behavior of the animals which absorb them. Now, in the context of this list of criteria, I would add only one other descriptor which is not yet commonly mentioned, which is biodegradability. Now, this is understandable, as the driving concern of microplastics is generally an environmental risk due to the long-term build-up, which would not necessarily be problematic with truly biodegradable materials. However, with degradation time scales being of the order of weeks or months, they may disappear quickly from the environment, but may still produce many short-lived particles which will still have a lifetime of relevance to living organisms. Finally, the natural conclusion to the previous slide on the components of possible definitions is to give a brief mention of the actual definitions, at least those which I'm aware of, which have effectively developed into a form suitable for use in legislative action. The first relates to the bans on microbleeds below 5 millimeters, which have been unilaterally undertaken by many countries and which use a variety of similar definitions, although some details and terminology are varied. More recently, and perhaps more closely linked to microplastics in relation to food, is a definition for the use in the monitoring drinking water adopted in California. Now, in Europe, there's still no direct equivalent, but important steps forward have been made with definitions such as those developed by ECHA for use in the proposed restriction on intentionally added microplastics in consumer and industrial products. In relation to this is the recast of the European Drinking Water Directive, which requires the future adoption of measurement methods which at the moment are not specifically defined, but presumably this will be developed in the near future, as methods should be adopted by 2014. My apologies for the delay here. Now, having considered the basic points of defining a microplastic and considering that for practical purposes, this must include sizes from 5 millimeters to a lower size range, which could be as low as 1 millimeter, I would now consider what is the current status of the methods which can be applied for detecting such materials. The figure shown by Schwafertz, although published in 2019, is a fairly good illustration of the situation which still exists today. Basically, for the detection and identification and enumeration of microplastics, the optical diffraction limit remains the dominant factor in dividing the measurable from the non-measurable, with the barrier being around 1 millimeter. Although the submicron range is not totally without methods, the approaches available are early stages of development or require a combination of methodologies in contrast to the micro-size range, where the dominant methods, micro FTIR and micro raman, can both identify and enumerate the presence of microplastics. Now, in considering the analysis of specifically microplastics, the field is dominated by the particle methods based on optical detection to give particle number, size, and with the exception of fluorescent microscopy, also the polymer composition. Now, beyond the optical methods, the only commonly used methods are those based on GCMS, which can identify most polymers, while LCMS can be used, liquid chromatography can be used for a selected number of soluble or hydrolyzable polymers, such as PET. The first method which I would describe is the simplest and least expensive method. It exploits the special properties of a fluorescent dye known as Nile red. The important feature of this dye is the fluorescent properties which change depending on the hydrophobicity of its local environment. In practice, the dye is weakly fluorescent in water, where the presence of more hydrophobic solvents increase the fluorescent intensity, as well as modifying the emission spectrum. In the photograph on the left, the dye is dissolved in a range of solvents, which viewed under natural light show a range of colours depending on the solvent used. When illuminated by UV light or near UV light, these differences are seen to be greatly enhanced, with the aqueous solution showing only very weak fluorescence. This unusual response of the dye to solvent in different hydrophobicities is observed in contact with solid materials with different hydrophobicities and provides a simple method for distinguishing microplastics from less hydrophobic materials such as minerals. Here we can see an example. It shows on the left an optical image of a mixture of sand minerals with microplastics viewed under visible light. Now, when these samples are stained with applied Nile red and observed under UV light, you can see in the figure on the left the dramatically different image in which only the plastics themselves remain visible in the image. This method has the obvious disadvantage that it cannot distinguish plastic material from other hydrophobic materials, and it gives no information about the type of plastic, and in the case of aged, coated or surface modified modified plastics, unpredictable results can occur. Now, while the basic method can give false positive and negatives, the reliability can be improved by the use of optimized staining procedures and by the use of counter-staining to mark some natural polymers. More recently, the fluorescence lifetime spectroscopy has been used in this method and has shown that the nature of the underlying polymer may make detectable differences to the fluorescent signal, potentially improving the specificity and the reliability of the method. Overall, the method is simple, rapid, modest cost, but risks a lot of false positives and negatives. Unfortunately, it provides little or no information on type of plastic. The next method I've described is micro-FTR, which is one of the most common instruments used in microplastics analysis. The technique exploits the fact that polymeric materials interact with infrared light, and certain wavelengths or wavelength bands are absorbed depending on the type and quantity of the molecular bands in the material. These absorption bands, when measured across a broad length of wavelengths, produce an absorption spectrum, which is characteristic of the materials being analysed. Now, when this type of measurement is combined with optical microscopy, it becomes possible to restrict the area of sample from which the IR spectra is obtained, obtaining a localized signal which can be used to identify the composition of individual particles of small size. Now, to illustrate the use of micro-FTR and its limitations, I've an example shown which was obtained using polystyrene particles in the size range from 5 to approximately 50 microns using a system equipped with a single element detector. The local chemical map was made by point-to-point scanning a 50 micron area and analysed to derive a chemical map based on the absorption band characteristics of PMMA. The particles were PMA, not polystyrene. Comparing the optical and chemical images shows that the particles the size of around about 10 microns can be distinguished, while the smaller microplastics, although visible in the optical images, cannot be detected in the chemical image. This illustrates one of the main limitations of FTIR, which for routine measurements would be limited to sizes around 10 microns, but for practical purposes and speed of measurements, a size of 15 to 20 microns would be more realistic. Better resolution can be achieved by the use of ATR crystals or combining it with multi-element detectors such as focal plane arrays. But these better resolution higher scans are achieved at the cost of significantly increased complexity of the instrumentation and cost and reduced throughput. Now, the main rival to micro-FTR is raman. Now, the raman method is based on the measuring the inelastic scattering of light by a material, which provides information about the molecular structure. Now, when an intense source of monochromatic light, such as laser light, shines on the material, the scattered light is mainly at the same wavelength as incident light, but due to some inelastic scattering, a small fraction of light has a lower or higher wavelength due to interaction with the molecular bonds of the material. By measuring the difference in the wavelength of light between the inelastic scattered light and the incident light, it is possible to produce a characteristic Raman spectrum, which is a characteristic of the material which is being analysed and can be used to help identify the material. Now, when this particular type of equipment is integrated together with an optical microscope, which allows the very fine focusing of the laser, it becomes possible to acquire this Raman spectra from very small regions of the samples. And by scanning and mapping, it becomes possible to produce chemical maps of particulates and materials over areas of microns, hundreds of microns, or larger. This example here shows scanning over an area of about 100 microns of a mixture of polymers, showing how after evaluation you can identify specific components within the mixture, which, when individually compared to spectral libraries, allow the identification of the polymers which are actually present. This is a powerful method, but it's complex and has a fairly high to medium investment costs. It has the advantage of having a lower detection size than the FTIR, and is very useful for identifying specific plastics. Unfortunately, the method is fairly slow, and in some cases, the presence of additives or colorants may result in fluorescence, which completely covers the spectrum, making it impossible actually to identify the material. Now, to give an example of these two techniques, I'll show a very basic example, which is an elementary product which is commonly used, which is sea salt. I chose this particular example because it is a product which in theory is potentially likely to contain some traces of microplastics. Now, the simple preparation here is obviously very, very simple. In this case, it's simply dissolution and filtration, possibly with a prior step of density separation to reduce some of the heavier mineral materials which may be present. Once this is done, the analysis can be done either as single point measurements of individual particles, which can be identified optically, or by chemical mapping. The choice of which method to use depends very much on the instrumentation available, the speed you need, and a number of factors involving also time and resources available. Doing such analysis using Raman microscopy takes quite a significant amount of time. In this particular case, this analysis which is undertaken, it requires about 1 minute collection time for each spectrum. This was in part longer than usual because we were attempting to get a large spectral width to be able to identify also the inorganic materials rather than concentrating only on the parts which is more specific to the polymers. In this particular case, it takes several hours to analyze a few hundred particles and then analyze them. In the case of FTIR, we found it was easier actually to use chemical mapping directly, as this proved to be much faster and was easier to automate with our particular system. In this case, we find results which very similar to the Raman, which was basically that there were very, very few polymer particles in proportion to the number of inorganic materials. In reality, we only found a very small single-digit number of polymer particles amongst many hundreds of particles actually analysed. Now, this indicates the lack of contamination by microplastics. It also shows the problem of characterizing materials where you have to analyze very large numbers of materials to actually get a statistically relevant amount of information from the particles available. Obviously, for such work, it's important also to do some quality control, and for this we have also made systematic blanks. And in this case, we only found one single particle of relevance. I'm running out of time here, so I will actually just skip over what was the other materials found. I will just add here very quickly the situation of doing such analysis also with more complex samples such as that extracted from mussels. In this particular case, we had to look at an enzymatic process, as this was much less likely to damage the materials. And as a result, we had to develop quite a complex protocol involving multiple enzymes. As you can see here, this is a very complex multiple-step process, which is relatively complex and potentially expensive to use. Although this was effective, it would be desirable also to be able to do this by a more chemical process. And I look forward to a later presentation, which perhaps will give indications of the capabilities of chemical processes, also for small particles in the nanometer range, as we were trying to do here. The other method, which is commonly used for nanoplastics, is GCMS. Now, this particular method uses the pyrolysis under a net atmosphere of the material and uses glass chromatography mass spectrometry to fractionate and identify the characteristic fingerprint spectra of the materials. This technique allows you to measure fairly small quantities of materials of the order of half a microgram, which corresponds to single particles about 50 to 100 microns. And it can also give information on additives, but unfortunately gives no information on particle size or size distribution. The advantages of this particular method are it's a powerful tool for detecting small masses, but it has the disadvantage that it can be quite difficult to actually calibrate, and in some instruments it can actually be quite difficult to handle the samples because of the very small vials which are used in the instrumentation. An important practical consideration is that the basic GCMS instrumentation is available in many analytical laboratories, and this must be upgradable to pyrolysis at moderate cost. A question which has to be asked is also the relative performance of the methods. Now, having described the common methods, the question which comes up is which is the best? Obviously, there's not a simple answer to this, but in the recent study by ICLS study by Muller, some attempts have been done to do this, in which the various techniques were used to analyze a single type of sample containing no mixture of particles with different compositions and size. It can be seen that the performance of the various methods depends strongly on what you want to measure and what size range is under examined. No single method could actually be considered optimal from this evaluation. Now, another point of relevance is the availability of different methods. Now, in a recent JRC interlaboratory comparison, in which there were more than 100 participants, we provided samples containing known masses and numbers of particles, and the participants were asked to use whatever of their techniques they considered most appropriate to measuring the mass or number of particles. Now, I won't present any more data about this other than just to show the distribution of the methods actually reported. As we can see, the use of FTIR microscopy is by far the most abundant, followed by raman and fluorescence microscopy for particle number. It was noted that there were relatively few techniques used for mass determination, and in particular, the pyrolysis GCMS, which is the most commonly reported method in literature. Only 2 examples were actually reported. Here I'll say a little bit about some of developing methods. These are recent, basically upgrades of existing methods, such as using higher power cascade lasers for micro FTIR, raman FTIR, the development of optical cells for online analysis of liquids, coupling the detector to, for example, nanoparticle fraction methods such as field flow fractionation, show promise. GCMS and its related method of TED GCMS offer interesting possibilities for automation with simplified sample preparation, as described with the pressurized liquid extraction, which would allow larger total sample masses to 1 gram or more. AFM methods, which you can permit IR and FTIR to move towards the submicron range. Another factor which is in development is also automated measurement and data evaluation. This is going to be very critical to save time and also to reduce the, let's say, user input and increase the objectivity of the results. Now, I will come on to a little bit about the nanoplastics. Now, the previous discussions all cover mostly the micron range, but for smaller particles, very few metals exist. Fortunately, over the last decades, the development of nanomaterials has provided some prospects for instrumental methods which could be adapted to nanoplastics. Here I've illustrated some of these techs: electron microscopy, single particle detection, ensemble optical methods and sizing, as well as particle size fractionating methods such as field flow fraction. Unfortunately, none of these methods are directly applicable due to the difficulties in specifically identifying polymers, but I will show some of the methods may be adapted or combined to provide partial solutions to the nanoplastics analysis issues. Okay, here I'll show you an example of where a modification of electron microscopy can be used. This particular example shows an electron microscope which is also equipped with an ion beam, which allows controllable etching of material from the surface. And at lower flux beam can also substitute the usual E-beam as a source of the secondary electrons which are used for imaging. We have found that using this type of system, imaging done by the gallium source, results in interaction of plastics, which gives a very, very greatly enhanced contrast in the electron images. As you can see by comparing the insert, which is normal SEM imaging, with the larger image, which is obtained with the gallium, which clearly shows the presence of the spike of polystyrene nanoparticles, which was placed on this material, which was cellular tissue extracted from muscles. In a similar way, the technique can be used to erode away covering materials and reveal underlying materials here. In this case, we can see how it shows plankton skeleton, or in the lower list, the polystyrene nanoparticles, which were previously largely hidden by inorganic material. Another technique which we have been exploring is the use of a single particle detection method, known as single particle extinction and battery. This particular method, in contrast to most optical methods, gives information on individual particles and also gives information on their optical properties. This gives a possibility of making it more specific to microplastics or nanoplastics, because it can be possible to distinguish it very often from the background matrix, which confuses many other optical techniques. Now, an example here can be seen in which we have taken three types of water: tap water, molecule water, and mineral water, and spiked these with the nanoparticles of the polystyrene. When these are analysed to show the different populations, i.e. the background matrix and the individual particles, it's possible to extract information about the spikes and to get information on the particle number, their size, and also on their optical properties, which can help to confirm their properties. You've stopped. So,
yes, sorry, Douglas.
I have only three more slides.
Yeah, sorry, but I have to inform you your time is out, and I think we have to confer some
Unfortunately,
of your...
I had a lot of problems because I've got this constant, I'm hearing my own voice coming back after 3 seconds, and it's very, very confusing.
Sorry about that, but I'm afraid I cannot help you with that. So
can I just say the concluding remarks?
Yeah, sure.
I would just say that Microplastics basic instrumental tools are available for size, number, identity, and while for nanoplastics, no routine instrumentals yet exist.
Okay,
I'll just leave that.
Yeah, I'm sorry for this, but in respect also for the other speakers, I think we have to continue.
No, I apologize.
So I'm sure we will discuss this a lot further tomorrow. I'm sure you will have time to come back to some items.
Yes.
So thank you for a very comprehensive and speedy talk. Our next speaker is Julia Süssmann from the Max Rubner Institute in Germany. And the title of her talk is Evaluation and optimization of extraction methods suitable for the analysis of microplastic particles occurring in the edible part of seafood. So please, you have the floor. 20 minutes.
Okay, thank you for the kind introduction and the opportunity to present our microplastic research at this conference. My name is Julia Süßmann and I'm from the Max Rubner Institute, the Federal Research Institute of Nutrition and Food in Germany. Research at our institute focuses on consumer health protection in the nutrition sector and advises the Federal Ministry of Food and Agriculture in this area. Our micro and nanoplastic research currently focuses on the analysis of small plastic particles in seafood, and today I want to present to you our findings regarding sample preparation procedures. Small plastic particles can be taken up by aquatic animals directly or indirectly. When those animals are consumed as seafood, these particles may be introduced into the human food chain as well. Furthermore, microplastics might enter seafood products, for example, via packaging, exposure to dust, or during processing. These particles can translocate from the gastrointestinal tracts into other tissues. Additionally, potentially hazardous chemicals such as additives or persistent organic pollutants can leach or migrate from the plastic particles into edible tissues. Consequently, microplastic might pose a risk for the safety of seafood products. However, the extent of microplastic occurrence in seafood products and the human exposure towards small plastic particles via consumption of seafood currently is still unknown. But why is that? There are numerous studies investigating microplastic occurrence of various marine species worldwide. But if we want to compare the results of different studies, we face certain difficulties. Some studies apply sample preparation protocols where plastics might be degraded or lost. Some studies don't identify the particles at all or only a subsample, and thus are prone to misidentification. Not to mention the differences in resolution or limits of detection of all the different analytical methods applied for polymer identification and so on. In short, we need harmonized and validated methods for generating reliable and comparable data. So the aim of our study was to contribute to method harmonization by evaluating sample preparation procedures for isolating microplastic particles from the edible part of seafood. This process generally starts with a digestion step in which the sample matrix is dissolved chemically. Here we have to consider that a broad range of matrices must be sufficiently dissolved while simultaneously not degrading plastic particles to a significant extent. Next, all remaining solid particles are isolated by filtration. We had to consider which filter pore size has to be used regarding the size of particles to be retained, but also the duration of the filtration as well as the filter material, depending, for example, on the reagents used for digestion or analytical procedure applied afterwards. Then the particles had to be analyzed. We focused mainly on the most commonly applied methods: microscopy, FTIR, raman, and pyrolysis GCMS. Here we had to consider that the matrix is removed sufficiently for enabling the detection and identification of polymers. Lastly, during the complete procedure, we had to consider avoidance of procedural contamination with plastic particles and possible particle loss during handling, for example, due to adherence of particles on labware surfaces. In the first step, we evaluated existing protocols for microplastic isolation from biota. We conducted a literature research and chose digestion protocols that were mostly applied for dissolving gastrointestinal tracts of aquatic organisms. We established criteria to compare the protocols based on their performance. Basically, the respective protocol should enable filtration of the complete sample with only one filter of the pore size of approximately 1 micrometer, so the protocol should have a high efficiency. However, degradation of plastic particles had to be avoided and the integrity of the polymers should be conserved. Finally, the protocol should be suited for routine analysis, thus high performance regarding digestion time, number of steps, and reagents costs was preferred. We compared protocols of different approaches, including the application of acids, bases, oxidizing agents, enzymes, and combinations thereof. After all, the two-step enzymatic alkaline approach was the most promising protocol compared to other approaches, as it had a high digestion efficiency for different matrix types and did not degrade most synthetic polymers to a significant extent. After the evaluation, we optimized the enzymatic alkaline approach, especially for improving the efficiency and the integrity. We also checked the digestion efficiency for a broad range of seafood products, for example, differing in their fat content. In the end, we tested whether the protocol was suited for quantitative isolation of microplastic with a preliminary in-house validation in fish fillet. In the following, I want to present you more details on our optimization and validation. First of all, we addressed polymer integrity, so we checked the recovery of polymer mass after enzymatic alkaline digestion. However, if changes occurred only in a small surface layer of a few micrometers, the weight recovery would not detect those changes and loss of small particles would remain undetected. Consequently, we also assessed the projected particle area where we could observe a significant decrease for PET, so we reduced the temperature of the alkaline digestion step. Aside from polymer loss, the chemical composition of the particles might be altered by enzymatic alkaline treatment. So we assessed polymer identity of virgin plastic particles with FTIR, Raman, and pyrolysis GCMS before and after the application of our digestion protocol. Significant differences in the chemical composition were only observed for polyacrylonitrile, though. After optimizing chemical digestion, we wanted to improve the filtration process in order to increase the filtration speed and prevent clogging of the filter. Therefore, we first considered the filter pore size. Filtration with filters of a large pore size was much quicker. However, small microplastics are lost, and current studies imply that the number of microplastic particles increases with decreasing particle diameter. Independent from the pore size, the filter material also had a great impact on filtration speed and clogging. Here we see matrix residues of each 10 gram of digested herring fillet on filters of different materials with a common pore size of approximately 1 micrometer. Another aspect to consider for filter material choice was which sample preparation or analytical procedure would be applied. Some filter materials might be degraded by the digestion reagents, like cellulose acetate by alkaline solution. Or, for example, thermal analysis might require the application of inorganic filter materials such as glass fiber filters. However, not only the chemical composition of the filter material, but also the filter structure has a significant impact on particle isolation. Multi-layer or fiber-type filters, such as the often used glass fiber filters, might lead to an underestimation of particles when they are hidden in the depth of the filter. In contrast, single-layer type filters have a smooth surface with pores of a defined size, which shows a good performance for retaining fragments, but may also lead to a loss of fibers that can pass the pores lengthwise. When applying imaging techniques, the focal plane of the particles should be considered as well. So when using multi-layer or fiber-type filters, confocal scanning might become necessary for obtaining sharp images of the particles. Incomplete separation of nano from microparticles might pose a problem in future studies, as we observed aggregation and adherence of nanoplastics in the much larger filter pores due to physical interactions. As of now, we cannot recommend an ideal filter that overcomes all challenges at once, and further research is required on this topic, including the isolation of nanoplastics. As small plastic particles can be found ubiquitously, procedural contamination of samples during sample preparation and analysis might occur. Therefore, we investigated probable sources of microplastic contamination, such as reagents, glassware, or deposition from air. We observed that insufficiently cleaned glassware contributed to procedural contamination the most. Rinsing with filtered liquids or heating the glassware reduced the number of particles significantly. Even after filtration of reagents or solvents, large numbers of suspect particles sometimes were still observed, as can be seen here for pre-filtered pepsin solution from different suppliers. If large numbers of plastic suspect particles occur, testing reagents from different suppliers is therefore recommended. During our tests, contribution of particles deposited from air was small. However, working in a laminar flow box was still preferable to working under a fume hood. We had best results regarding prevention of particle contamination when we were working in a laminar flow box and cleaned all glassware reagents and filters thoroughly. Nevertheless, even with the most thorough measures for contamination prevention, we were able to apply plastic suspect particles with diameters in the lower micron range were still observed in blank samples. This emphasizes that monitoring of blank samples during sample preparation is recommended. The final sample preparation protocol is shown schematically on the left. First, the sample matrix is dissolved and then filtered with either one large filter in option A to be analyzed directly, or pre-filtered using a smooth filter in option B for pre-concentration of the particles, which are then rinsed off onto a small filter, for instance for the application of imaging techniques. Depending on the sample matrix, the filter can be treated further with solvents or oxidizing agents. For preliminary in-house validation, we applied the more complicated version B, as it was necessary for pyrolysis GCMS in our lab. First, we tested if polymer identification was possible after isolation from fish fillet with pyrolysis GCMS, as shown here exemplarily. Therefore, we spiked fish fillet with commercially relevant plastics. Qualitative analysis with spectroscopic methods was tested with Raman microspectroscopy exemplarily. For quantitative analysis, we assessed the recovery of spiked plastic particles of one polymer type with particles of 10 to 50 micrometers diameter. Due to low recovery rates of polymer masses, further research of pyrolysis GCMS quantification in seafood is still needed. Current studies imply that the abundance of particles increases with decreasing particle diameter. Consequently, it is assumed that the analysis of nanoplastics in food will be of great importance in future. Our first assumption was that nanoparticles will be separated from microparticles during filtration. However, our preliminary filtration tests showed that there is still a research need regarding other sample preparation methods for the isolation of nanoplastics. We also conducted first tests regarding concentration and separation of nanoplastics with asymmetric flow field flow fractionation. Regarding the detection limits of AF4 and pyrolysis GCMS for consecutive identification, however, still need further improvement. I want to close my presentation with a brief summary of our study. The optimized digestion procedure for microplastics from the edible part of a broad range of unprocessed seafood products was found to be a two-step enzymatic alkaline approach. Even when applying a thorough protocol for preventing plastic contamination, running blank samples for monitoring procedural contamination remained necessary. The choice of the filter and its material had a great impact on the filtration speed, the amount of matrix residues, microplastic retention, and particle detection. However, more research is still required on that topic. Finally, more research is also required regarding the sample preparation for the isolation and concentration of nanoplastics from seafood products. More details regarding our study are published in the paper mentioned down below. In the end, I want to thank all people involved in this project, especially my colleagues from the Max Rubner Institute, from the University of Hamburg, from the Technical University of Berlin, and lastly, I want to thank you for your attention, and I'm looking forward to your questions. And then here are the references.
Thanks a lot for a very nice presentation and very clear. Actually, I can see no specific questions for you. So if there are things you didn't have time to cover, or if you want to comment on something, you are free to do so. We have a little bit of time, but not much.
I think I covered all.
Yeah. Thanks. It was very clear. Then I think we are back on schedule. So I suggest that we continue with the next speaker, and that is Pietro Giuseppe Gucciardi, and from the National Research Council of Italy. The title of the talk is Raman tweezers for small microplastics and nanoplastics identification in liquids. So you have the floor.
Okay, thank you very much. And thanks a lot for giving me the opportunity to speak at this colloquium. And I'm Pietro Gucciardi. I come from Messina, Sicily, and I will talk about optical trapping and Raman spectroscopy for micro and nanoplastics analysis. Okay, so I will briefly highlight some of the technological gaps that are present in the analytical tools for nanoplastics analysis. Basically, Douglas Gilligan already gave an extensive overview, so I will be very rapid on this. And then I will show how optical trapping combined with Raman spectroscopy can help bridging this gap. And in order to do this, I will show examples on the analysis of model and environmental plastic particles, and then I will conclude. So we all know that between 3 and 13 million tons of plastic debris are released into fresh water per year. The question is that among this, an indeterminate fraction is nanometric sized. Nanoplastics have primary sources such as waterborne paints and 3D printers that turn up to be a quite relevant source and potentially very hazardous source of nanoplastics, and secondary sources that are basically given to the photothermal oxidation of larger particles. So microparticles will fragment into nanoparticles, and of course, to some extent, all of this will finish in our watery systems and will be ingested by animals or by fishes. Okay, I've seen, interestingly, that micro and nanoplastics can be found in drinking objects. And basically, it was in this very recent review published in 2021, I've seen that fragments of plastics, of small plastics, meaning dimension 5 to 10 to 20 microns, have been found in Germany in bottled water, also in beer. And very interestingly, in bottled mineral water in Italy, it was found that particles ranging down to 500 nanometers, meaning in the nano scale regime, have been found. So in drinks, we can find small microplastics and even plastics. Of course, as has been shown, nanoplastics can be absorbed by living organisms, as this Daphnia magna shows, in which it has been mixed with some fluorescent nanosite polystyrene spheres, and as we can see here in these green zones, there is nanoplastics. Okay, so basically we are fully covered for what concerns the particle size analysis. So we can monitor particles going from 10 centimeters to 1 nanometer using dynamical light scattering, nanoparticle tracking, optical microscopy, electronic microscopy, atomic force microscopy. The problem basically is when we deal with chemical analysis, so when we want to understand which material is composed this particle of. In this case, as we have seen, there are three election techniques that are FTIR, Raman spectroscopy, and pyrolysis GCMS. The question is that when we come to the analysis of single particles, then we have basically a limit, as it has been shown, to the 10 microns or 20 microns regime for what concerns FTIR. For what concerns Raman spectroscopy, we can even go down to 1 micron or even to 100 nanometers. Actually, for some materials, we have very, very good sensitivity that permits us to go down to this size range. And then the question is, of course, separating one or more particles, because there is the so-called diffraction limit in optical microscopy that prevents us to separate particles that are closer than, I would say, 250 nanometers. Okay, we can detect, but we cannot say if there is 1 or 2 or 3. So another problem is that we have a serious methodological gap if you want to measure particles directly in liquid. The examples shown up to now, I've seen that if we dry the particles, then we can analyze them, but when we go in liquid, we have serious problems to do this. Okay, let me show again. Raman spectroscopy, as we have seen, is a vibrational spectroscopy technique that somehow detects the sound of molecules. Okay, instead of vibrating the strings of a guitar, here we see the vibration of the nuclei. And since every molecule has a different fingerprint, a different tone, we can separate molecules. So we can perform materials recognition, structural recognition, and what is very important, we can have imaging capabilities, and this technique is non-invasive and works in water. Let me show you. Okay, micro Raman spectroscopy, of course, combine microscopy with Raman spectroscopy. And for example, we have this image, and based on these Raman spectra, these peaks that you see here, each molecule has its own fingerprint, and so we can unambiguously discriminate these molecules. Raman works well on dried samples, in liquid samples, molecular solution, and precipitated samples, but there are serious problems when we come to dispersion of micro or nanoparticles in liquid. As you see here in this cuvette, we have some dispersion of polypropylene microplastics in seawater. And interestingly, if we make a measurement of this solution, we compare to the same solution without the polypropylene particles, we basically see the same spectra. You see the red and the black lines are basically the same. Why this motivation? Because if we look at the microscopic level, we see that these plastics will be subject to Brownian motion. And if we focus the laser, you see that most of the time, unless the particles are very dense, the particles will be outside of the laser spot, and so they will not be investigated. And so this means that we basically will see the same signal of the liquid medium, basically the seawater. This means that the dispersion of sparse particles are hard to be analyzed by Raman because of limited integration time. Of course, I'm discussing about investigation of particles already in liquid. So how we can go beyond? We can use optical trapping techniques. So the idea is that we somehow use light to trap each particle. So once the particle is in the focus of the laser, we can Raman analyze it for as long as we want. So light can be used to trap matter on different scales, from the micron scale, the Nobel Prize awarded to Arthur Ashkin recently, to the atomic level, another optical trapping Nobel Prize given in 1997. So we can use light to manipulate particles basically from the micron scale, means tens of microns, 1 microns, basically to single atoms. Okay, so what we basically do is use so-called optical tweezers. What is an optical tweezer? It is basically an inverted microscope that uses a high numerical aperture objective to tightly focus the light on the focus, and as a light source we use lasers. So what typically happens is that we inject this laser into the high numerical aperture objective. We generate a focus whose dimension is of the order of 300, 400 nanometers, and in this strong field gradient we can trap particles. Why do we trap particles? Because when we interact with light and matter, there is some conservation of the linear momentum. Okay, it's a sort of action-reaction. So if we calculate the optical force that acts on a particle, this is composed by three components. The most important are the first two. The first one is the intensity gradient. The intensity gradient force is so-called because it attracts the gradient of a field. So if we tightly focus a laser, then we have a gradient of field and the particle will be attracted there. Here you will see some carbon nanotubes that when the laser is off, they fluctuate normally, and then when the laser on, you will see they are trapped. Okay? So if this intensity gradient force is strong enough, we will trap the particle. Otherwise, if we have the radiation pressure that is stronger, we will see some comet effect in which the particles will be pushed away from the focus. So the question is how to do Raman tweezers. Of course, we combine an optical tweezers plus a Raman detection tool, so another laser or the same laser, so we can make 2 beams Raman tweezers or 1 beam Raman tweezers, and basically what happens is the same. So in a single beam Raman tweezers, as we show here, there are 3 components: laser sources, optical tweezers, and spectroscopy. So the laser sources launches the laser goes to the optical tweezer section, and from here it is focused on the sample compartment. Sorry, I don't see the line. Okay, on the sample compartment. When it is on the sample compartment, it is tightly focused, and here you see the movie. This is a microplastics that when the laser is off fluctuates. Now it is on the laser. Now the laser is off. It fluctuates. The laser is on. It is trapped. When it is trapped, you see that we can bring it wherever we want, since the sample compartment is on a stage. So once we have trapped it, we can detect the backscattered light and send to the spectroscopy, and for example discover that this is a polystyrene sphere. Okay. So can we trap nanoparticles, micro and nanoplastics? Microplastics can always be trapped since their refractive index is larger than in water. For nanoplastics, since there is Brownian motion, the Brownian motion will tend to push the particle away. But if we use a laser source that is strong enough, for example, for these 100 nanometers polystyrene at 633, we need power higher than 15 milliwatts, we can trap them, okay? So let's see some examples. So again, the same move as before. The particle fluctuates, we trap. Once it is trapped, we can keep it in the trap as long as we want, and we can get the Raman spectrum. Here we see the optical images, the top images of particles going up from 50, 90 nanometers, half a micron, 1 micron, 2 microns, and 5 microns. And down you see this, the corresponding Raman spectra. So you have more intense spectra as the particle is larger. From what is important is that 500 nanometers PS particle can be investigated in a short time, 0.5 seconds. So the technique can be quite efficient. Based on some model, we can understand if the particle is a single particle or if it is an aggregate. Let's focus a little bit on the single particles. Here, for example, we have PMMA particles, 300 nanometers, and we can distinguish from the Raman spectrum if we have 1, 2, or 4 particles. Of course, the signal is proportional to the number of particles. You see the red line here that fits the experimental data. And we can verify this just by looking at the number of particles that are trapped. In this case, the particle fluctuates, now it's trapped, we release it, we understand that it's just one particle, and we can do this with 2 and 4 particles, okay? So another thing that is very interesting is that we can, for example, produce nanoplastics or microplastics by just grinding stone, and then disperse these in water, and of course detect them, and measure them, their size, and detect their chemical species based on the Raman spectrum. And for example, if we mix them to seawater, we can distinguish these fingerprints of the plastics from the fingerprints of the microsediments. So unambiguously, we can distinguish microplastics and nanoplastics from seawater microsediments. We can do also this, for example, in a sample we had some dispersion of polypropylene particles down, the spectra down, and we can distinguish this from nylon particles that we discovered dispersed. Finally, let me show 2 environmental samples. One is a cap of a bottle that was found abandoned from years along the lakes of Ganziri. We discovered that it was very brittle, so if we fragment it, and we fragmented it in water, we can have particles that are in the micron scale. And from the Raman spectra, we can distinguish what is the polyethylene, the material of the cap, from other particles, like anatase due, for example, to the earth that is found, and in which we found the cap. Let me show another important example, another nice example. In this case, we discovered these you see here a paint bucket. The paint bucket, again, was very hard and very brittle. You see the optical images here that produce nanoparticles. And we have microparticles, small microparticles, I mean, a few micron range, and then even some nanoparticles. And then if we do this in water, for example, if we break this on the lake, we will disperse this kind of materials in the water, and we can trap them one by one and discover which is their chemical nature, ranging from propylene, rutile is basically the materials composing the paint. So again, the message is that when we break brittle materials, we can produce nanoplastics, and if we break these materials in water, then we can use optical tweezers and Raman tweezers to trap them one by one and analyze them. With this, I conclude. So we have shown that with optical tweezers, we can analyze polyethylene, polypropylene, PT, microplastics, and nanoplastics of different materials. Single particle sensitivity has been shown experimentally down to 300 nanometers diameter. And detection of aggregates of 50 nanometers particle has been shown, some tens of particles. And finally, okay, we have made some observation on nanoplastics in weather environmental samples. Let me acknowledge, this is the final conclusion, that optical Raman tweezers can play a role if we are able, for example, to implement on this technique some concentration extraction and the trapping analysis, and so we can hope to have somebody on with an iPad in his hands, determining which particles are made of what and determining the statistics somehow in a food production line. This is a sort of dream. Let me conclude by acknowledging the great work that Raymond Gelibert has made when he was in IPCF. This work is a collaboration between IPCF, IFREMER in France, Université de Le Mans, University of Gothenburg, and these are the projects that basically funding this work, Microplastic. And let me conclude with this photo of our group. Thank you very much.
Thank you very much, Pietro. This sounds promising and optimistic. There's one question for you from Dr. Gucciardi, and sorry for my pronunciation. I hope it's correct.
No, it's perfect.
Oh, thanks. Thank you for the nice presentation. Could you comment on the limit of detection in concentration with the optical tweezers / raman?
Cool. Esatto. I mean, I think this is one of the big issues, in the sense that consider that when we prepare our samples in this very rude approach, we analyze volumes that go from 10 microliters to 80 microliters at a time. Okay, so if you don't have at least 10 particles in such a volume, the mission is quite desperate. How to go beyond? It has been already shown by the group of Ivleva in Germany that it is possible to implement such technique in a stream of fluid. So the idea is that you have some microfluidic chip or whatever you want, some stream of fluid, then you see at the microscope some particles passing. If you see them, you can trap it and analyze. And from this point of view, of course, you don't have to prepare each time your 10 microliters samples, but you can, in principle, work in a stream of fluid and then evaluate which are the concentration limits. I have to say that we started this project with the idea of detecting nanoplastics in microplastics in seawater. Then at a certain point, we discovered that the typical concentration are 1 particle in 1,000 liters. So I think that with this concentration, there is no way to apply this kind of techniques unless we are able to strongly concentrate the particles. So if we are able to filtrate and strongly concentrate the particles in order to have a concentration of a few particles, I would say in a milliliter, okay? Some particles in a milliliter, then from that point of view, we can think about using this kind of techniques.
Thank you. There's another question for you, and it's to everyone, but I guess you are the one who can try to answer. So could Raman tweezers be combined with flow cytometry?
This is exactly what I was mentioning in the work of Dr. Ivleva at the Technische University München, if I'm not wrong. And the idea is to basically use optical forces somehow to confine the particles and then analyze them by Raman. Of course, it's a Raman spectroscopy technique, so it has the limits of fluorescence, as Douglas was saying. So if we have fluorescent particles, we will not detect its Raman signal, but its fluorescent particles. But on the other hand, we could, for example, think about using these techniques mixed with dye staining. There was a very interesting paper that was cited concerning the detection of plastics that had been stained with dyes, nile red, methylene blue, whatever. And we can think about using these Raman. In this case, it's not Raman tweezers, it's fluorescent tweezers, to analyze this kind of materials. I mean, I see that added value is that we don't have to dry them, the particles. Okay, so if you want to analyze the particles directly in liquid, you have several problems with the normal Raman, But if you are able to chop the particle one by one, then you can do this kind of analysis.
Thanks a lot. I think
Thanks
there
a
are
lot.
no more questions at the moment. So it's time for lunch. We will break now and then we will start again at 2 p.m. Central European time, of course. I wish you all a nice lunch and look forward to see you again at 2. Thank you.